Yeah, good morning, everyone. It's good to be back here in person again, finally. I've been really excited for this. Yeah, there's an ongoing theme here with my talk. So the last two times I spoke here, I did speak about puzzles, about logic puzzles, and then about solving Rubik's cubes. So those were using relational programming and group theory, respectively. So we're continuing with that sort of theme and talking more about problem solving, like the thought process behind problem solving, and specifically in a live coding kind of a context. So for some background context to this, during the pandemic, I started doing more experimenting with live streaming live code as I solved some problems. And you know that was for various reasons, but the long and short of it is, you know, I want to practice communicating code as I do it, right? So this helps with pair programming with any kind of tech demonstration you're doing, perhaps an interview, and of course a situation like this, a talk, which might sometimes include live coding. So I'm just going to get started right away with the highlights today. This is what I'm going to try and convince you of. And one is that you should be embracing worksheets for more exploratory problem solving. So I think they're kind of underrated. Perhaps maybe on the data science side, maybe people are using Jupyter more often and know the benefits of that. But I think they really should be used in a lot of contexts, and even perhaps attached to your library that you're developing or your production code base. And you should be pair programming more often. That will be self-explanatory here in a bit. You should try recording yourself. This was a really interesting exercise for me over the pandemic. So it wasn't just live streaming, but when I stream, I have all these recordings of myself that I can review, right? So I have a couple hundred hours of footage to review of myself solving problems, and I was able to take out a lot of insights from that. And of course, that Scala 3 is an excellent medium for this kind of interactive problem solving and for communicating your problem solving process. And we'll go more into all those points later. Okay, I already mentioned this a little bit. This is my context for why I went into live programming, live coding. And one thing I didn't mention here is it is fun to share and discuss puzzles or a problem that you're solving. I do very much enjoy pair programming with people and doing this collaborative problem solving kind of a thing. I also enjoy puzzle hunts, that kind of a thing. And it was a nice thing to do during the pandemic. And yeah, here I've listed some of the benefits, but I'll move through these slides pretty quickly because we're going to end this with a bit of a live coding demonstration. But yes, I've touched on recording yourself and being able to watch that footage. I've been able to catalog, so I've made a lot of mistakes, and this is not going to be in this talk. This will have to be a follow-up blog post on all the mistakes I've made. But I've been able to catalog a lot of common coding and reasoning errors that sort of cut the flow of your process here. And I've been forced to try and find ways to maintain clarity of thought and explain these ideas, explain what I'm working on as I'm working on it, which is important for collaboration, not just when you're demonstration, but when you're working with a coworker, and a colleague doing whiteboarding or whatnot. Okay, so in this context where you're live coding, you're trying to explain this to an audience, you're trying to make sure they understand and they're keeping along with you, there are a few things you want, right? So you want the ability to prototype rapidly, get your ideas down on paper, start something, start getting those ideas on paper. And then once you have a start there, you want to be able to expand it, expand upon those ideas, maybe change those ideas, and you want to be able to do this fluently and and while maintaining, the correctness of your code, maintaining the making sure it's still understandable. And since problem solving is not always like a linear process, you want to be able to like backtrack, think about new ideas, change your ideas, go back to what your ideas were previously, etc. Right? There's kind of a tree traversal as you're searching for a solution. And built-in testing also facilitates that. And that comes alongside this ability to demonstrate what you're thinking as you're going, right? So if you're able to test things kind of in line as you're going, then you're able to demonstrate what it is you're trying to do. And that's beneficial for your audience, of course, but it's also beneficial for yourself in the same way that rubber ducking can be. And of course, we want to minimize debugging, right? It's not fun for either party if you're kind of stuck there scratching your head at a problem, right? It's awkward and uncomfortable for the person who's doing it, and it's awkward. It can be awkward for the audience as well, right? And we don't want that. We want a fluid, a fluent, lucid problem-solving process. So these are the goals that are driving me when I think about my environment and my tooling, and why I use what I use here. Of course, I can touch briefly on this on Scala as a medium of thought. This has probably been covered plenty by other people in other talks, but it's the same old. You have type safety that lets you offload some of the thinking to the compiler. It lets you kind of encode your ideas into the source code, which makes it easier for the environment to assist you, but also easier for you to see where your train of thought was, because you don't want to be kind of thinking about what you were thinking earlier when you're trying to think of new ideas and problem solving, right? So it communicates the ideas to whoever you're talking to, and to yourself, a note for self for later. And of course, the tooling is great. The interactive environments, I'll get into that. And of course, Scala 3 as a language is very kind of flexible to play with. You can scale from different constructs as you're changing your approach to solving a problem. And of course, that's been gone over plenty. So that's not what this talk is about today. So I had mentioned in the last slide here, I'd mentioned these interactive environments. And what I'm going to be focusing on today is the Scala 3 worksheets. And there are a few ideas I want to bring in here, because I feel like this combines the benefits of some of these older ideas. So test-driven development. When Kent Beck wrote his original book on test-driven development, he'd mentioned an idea that he sees TDD as a way of giving programmers the benefit of the small talk environment, or of the environment and the interactive nature of it, right? So when he was going from a dynamic language to a compiled language, he was missing some of that benefit of being able to go into the REPL and explore these ideas as you go, and just test things out. You write a line of code, you see what it does, and then you keep iterating on that. And that was one of the reasons why he recommended test-driven development, was that the unit test being able to run on each compilation kind of replicates that, right? But now with worksheets, we kind of get that. We kind of get a REPL plus, right? So the Scala REPL is already nice, and of course, like a natural evolution of that was Ammonite with like the multi-line editing and whatnot, and of course, like now Ammonite in like Metals Worksheets. So it's still interactive. You get the results of all the code that you're writing right there in line. But now you have more flexibility to edit it, and you have your editor and all the tools that come along with that. So this kind of gives you like a lightweight way to test as you go, right? And then there's this idea of rubber duck debugging. We're all familiar. You might see how that comes naturally when you're rubber duck programming, or say you're speaking to someone as you're live coding, right? And that same kind of idea. So when you're writing all of this into kind of a worksheet from scratch and then going very iteratively and then explaining as you go, the worksheet makes it easy for you to be very iterative here, and you pick up some of the benefits of rubber ducking, where like you would catch on, hopefully. I mean, there are some cases where you don't. It takes a little bit of like thoughtfulness as well, but you catch. If you're explaining what you're doing to yourself or anyone else, you're catching on to these problems. And then, of course, there's the idea of literate programming from Donald Knuth, which is that this is programs interspersed with text. Sort of programs as literature, something you would read, and it would be a lot more instructive. But what Knuth found is also that the process of writing this helps understand. And now, you can certainly, worksheets are great for literate programming. You could do that. In the context of like a live coding demonstration, the literate part is your speech. So this whole idea of like pair programming with a worksheet, or live coding with a worksheet, reminded me of all these ideas, and seeing some of these all same benefits. Yeah. I had this idea of a whiteboard. It's kind of like an ideal whiteboard here, in that you have an ability to use it for demonstrations, but also write ideas down. Okay, so we're going to do a little bit of a demonstration and show how these these worksheets work. And let's see, I didn't have it pulled up. 2022 day, what is this? 12. Okay. So I've pulled up a problem here. Let me make it a little bit bigger. And there's a lot of flavor text in here, but the basic idea is that you're given a map, and you're given a height. So this is a grid map with height and elevations of various points on the map, and you have a starting position, and you have an end goal, and your goal is to hike up to this peak here, this E, in as few steps as possible. But now there are some rules here. You can't climb very vertically, so you can only go up one level. So for example here, from S, you have A, B, then you can go down to C, because C is one level above B, but you couldn't go up to Q or R here, right? So this is a simple enough problem. And I'll say this could be done with a much larger problem. What I would like to do, if I had more time, is to lay out a much larger problem and show how each of these kind of mistakes or debugging ideas can come into play. But this will have to serve for today as kind of like a demonstration of the idea. So here on the left, we have, on the right, we have the data set. So you can see, rough idea, like a lot of it's actually fairly flat. And then over here, we have what looks to be some sort of a mountain, where we have much larger letters in here, and different gradations. So let's start working on this. So we have a grid. So we probably want points. So I mean, first we could check that we've in the worksheet we could check that we've parsed that text file properly. So now we have a vector of strings, and we're just going to use that as a 2D grid of our map, right? So if you have grids where we're traversing through this, we'll probably want points. So we'll make a case class here. And we want a way to like check into this grid. Like so, if we have a point, what we're doing with these points is like traversing through. So we want a way to get other adjacent points to it. So we can just add that as a definition in here. So let's say we add an up, and that would be a new point. So we could just use the copy constructor. So we give x and y equals y plus 1. And because we're in a worksheet here, we can do some sort of testing. So 0.00. Again, this is like a trivial example, but this kind of thing you can do is as you're writing this, you immediately test it. So .u, and you get the 0.01. Okay. So we'll want that for like left and right. So this becomes a minus here. And then we have a left and right. And in this case, these just become x's. Left would be -1, x would be +1. And again, we could do like some sort of a test here. So like point 0.0.u.r. And look, so that looks like a bug. So we can look into maybe why that's wrong. Maybe let's just look at .r, see if we move to the right. And we're actually moving up here. So the error here is that we copy-pasted the y's, and we have x's here. And of course, like there's a benefit of like testing early and often. You catch this before it kind of is more confusing in the context later on, right? So we have those tests in there. We can just leave that and continue on. So we want to be able to find what we have. Like we have a starting spot, and then we have. So we have to be able to find that. We have to be able to compare the elevation of certain places. So let's do that right now. So def elevation given a point. And then we could just index into the grid. So grid p.y and then p.x. So let's look at our test data here. And 0.00 here should be A. 0.11 should be this B right over here. Let's make that, oh, we can't make it all bigger. So let's give that a test. And this test point, we've done so much, so let's just give it a name. Val origin. And then we can test on it repeatedly. So elevation of the origin is A. And origin.down. And again, we have another error here. So what's wrong? This is probably, well, let's read it. It's an index out of bounds. So our conception of down is kind of different from what we're expecting here. So what we could do is invert all this, right? Plus, minus. Right, actually, we'll keep that there. And now we'll just use y as positive indexes go down, like in graphic programming or like a canvas, right? A dot down is B, great. And if we go to the right, we get B. And if we go to the right again, we get C. And there I'm pretty confident that elevation works. And I am using, so what I'm returning here is just a character, right? So I don't even need to translate this to a number. I can do kind of this, I can do a check like this. So let's look at that A. And let's look at the one to the right of it, so this B. And let's look at the elevation difference. So minus elevation, origin dot, or wait, we actually just want the origin, or here, we want the point to the right. We want the point to the right minus the origin, and that should be 1, because that point is 1 higher than this. So we know we can use this function here. Okay, so now let's look specifically at the problem statement. Was the fewest possible steps required to move from your current position to the location that should get you the best signal? Okay, so what I want to do with this, how I want to approach this problem here is kind of a flood-fill approach, right? So we'll look at our starting point or starting set of points, and we'll expand from adjacent pieces around there to places that are legal to go. And we'll just keep doing that. And this is a small enough problem that should be an efficient enough approach. It's at least worth a shot. Okay, so we have a starting point. Actually, before we do that, I think we want adjacent points. So we want the set of points that are adjacent to any given point, and we probably want to filter for if they are in bounds. So before we do that, let's do an in bounds. I like to do that this way, so let's make an X range. So we have grid. We'll just take the first element, head dot indices, and then we have a Y range, and that would just be the grid dot indices, and we can double check that. So this is 0 until 81 on the X, and we can see here in my editor that we are going to column 81. So I'm feeling comfortable about that. And to check if a point is in bounds, def in bounds, we can just say X range contains X, and Y range that contains Y. And again, as we're doing this, we can add more mini tests in here, right? Like you might be doing this because you're explaining it to a friend, or just trying to convince yourself that there isn't an error here. So again, we can do origin dot inbounds. We're getting an error here. The return value of origin is null, because actually origin we should define up higher. Okay. Okay, and if we go origin and then we go up, which should not be legal, that should be out of bounds. So we have a test there. Okay, so now we can get our adjacent. And we'll just say set UDRL dot filter inbounds. Dot inbounds, there we go. And again, we can test that. So origin dot adjacent, and we get those 2 points, and that makes perfect sense because it's in the corner. Okay, so now we're searching for a path. And what we're going to do here, let's have some sort of next function. So given a set of points, so def next, this is the set of points we just visited, and then we have kind of a current set of points. So this might be like an approach you might be familiar with. And in fact, maybe we don't do this right now. I'm jumping ahead because I know I'll probably go into this kind of a solution, but let's just say this goes from a set of points to a set of adjacent points. How am I on time? 25. I have 5 minutes here. There's a possibility that I skip to the completed version of this file, but that's okay. We're getting the idea here. So we would just take, we take the visit points, and then we map to adjacent. And since this is a set of points, this will get your set of adjacent points. And now we want to prevent going into an endless loop, right? So we're going to rename these actually. So this is now our current. We're going to have a previous. So we have another set of points. And we'll just call it current. Filter not previous. Okay, so this gets us everything in like an expanding ring around us. And now, of course, we want to test that this is okay. So let's say we had, just 1, 1 over there, and maybe we call next on it twice, or let's take a set of 2 points. So let's call next. Let's actually start at the origin. So previous is the set of just the origin. And then next would be, the current points would be just the ones adjacent to origin. Or that edge. And again here, this is actually a method. And here, we'll just do a diff against previous. Not quite. So if we map this, it should still be, oh, this is a flat map. We still want a single set. Right, and then we see, we're expanding here. We have this line of 3, and of course those are all valid because we don't have any high cliffs here yet. And at this point, I'm going to just go to sort of what this will look like here at the end, and what you might do in testing this along the way. So what I hadn't added here yet is an additional filter, again using that elevation function. Again, this whole next thing can be its own function that we were writing, and you can test that separately, right? And then if you're familiar with an unfold, then this unfold here can use that recursive function to continuously grow a set, right? And then it will return this lazy list of set of points that are the expanding flood fill, and our answer would just be to search this lazy list of points until we get to the end here. Anyway, that is my time for today, and I'll move on to questions. Thank you for coming.